Okay, section 9.3. Guess what? We're almost done. This is actually the last section we'll cover in this class. But a heads up, I usually do spend 2 class periods on normal distributions, so there is a little bit more material to cover here. So, to begin with, I'm going to consider a scenario where we have a bank manager measuring the time that various tellers take for their transactions. The actual numbers aren't here. I'm not going to really use. I'm just showing you what numbers are used. But you can see if we round to the nearest minute, there are 3 transactions that took that long. If we round to the nearest 2 minutes, there are 5 transactions that took that long, and so on. If I take and I plot these, if I make it construct a histogram, I get something that looks like this. And then from that histogram, I can take and construct my frequency polygon. So now I'm going to consider what happens if I was to take, instead of dividing this and rounding it to the nearest 1 minute, what happens if I looked at the nearest, I don't know, second? Or maybe I took a finer scale than that, to the nearest millisecond. Of course, I'd have to take more samples, because otherwise, you know, I'd have a really sparse-looking graph. I'd have something there, and then something there, and then something there. But if I was to just increase the number of times the number of samples I take, I would still end up with a very similar shape. I might end up with something that looks like this. You can kind of imagine maybe my histograms are going like that. So if I was to take and do this repeatedly and get finer and finer scales, then I would get my frequency polygon would actually start to have curves, or it would look like curves. And eventually, if I was to take and do this continuously, instead of rounding to any value, if I took exact values, I would end up with a continuous distribution. So one of the things to note here is that since we're dealing with probability distributions, notice these are this is a probability histogram, not a frequency histogram. So this is not, I'm not saying this is 1 and that's 3. This is instead 1 out of, what is that, 100? I think that's 100 measurements. 75, whatever. So this would be 1 out of 75, this one's 3 out of 75, that one's 6 out of 75, and so on. Since this is a probability histogram, I know that if I was to take and add the probabilities of each of these up, they should sum to 1. Because that's what we've seen with probability distributions. If you were to take and add all the different cases, you add them up, it should sum to 1. And the same thing is true here, even if I have a bunch of them. Or if I took that to the extreme and had a continuous distribution, the total area is 1. So what we're going to do here is we're actually going to be representing, instead of having individual bars and saying the height of the bar tells us a probability, what we're actually going to be starting to talk about is we're going to start saying the area underneath the curve is the total probability. Just a little bit of a look ahead. Alright, so the particular continuous distribution that we're going to be dealing with here is called a normal distribution. I'm kind of jumping ahead there a little bit. But a normal distribution, actually I guess it was at the top of the previous page too. This is what the shape of a normal distribution is. Sometimes it's referred to as a bell-shaped curve because it kind of looks like a bell. You can imagine the Liberty Bell, except the Liberty Bell has the, you know, then you have your ringer hanging out here, whatever. It's well, in any case, it's called a bell-shaped curve. With a bell-shaped curve, you have your mean right in the middle. At least the ones we're going to be dealing with have the mean right in the middle. Now, when we're talking about the mean of a continuous distribution, or especially with these normal distributions, instead of using x bar for the mean, we're going to be using the Greek letter mu. So this right here, this is going to be the mean. That's mu. And we're going to refer to the standard deviation size with a sigma. So we have mu and sigma to refer to the mean and the standard deviation. I know it's a little bit of a pain using x bar in some cases and sx, x bar and sx for some things, and then mu and sigma when we switch over here. But it really has to do with the fact that here we're dealing with a continuous distribution, and so that's why we're going to use the mu and the sigma. And it gets a little bit more, there is more reasoning besides that. That's just what I'm going to leave you with. There are, in the real world, definitely skewed distributions like this one. You can see our the mode, or the maybe not the mode, but the peak of our curve does not occur right in the center. It's not balanced about the peak, so we would actually say that this is skewed. We're not going to be dealing with skewed distributions in this class. We're only dealing with nice balanced normal distributions. Some examples of where you would see normal distributions. Talk about the heights of women or the heights of men. Interestingly, if you try to add those together, talk about the heights of women and the heights of men, if you were to overlay these, you know, the average height of men is just slightly above the average height of women. And if you were to kind of overlay them, you would actually get something that isn't quite a normal distribution. You might get something that looks like this, where it kind of takes a little slump and then it goes back up again. So sometimes when you're talking about these measurements, if you take a bunch of measurements, the original thing might not look like a normal distribution, but then when you break it down into its constituent parts, you know, this would be the distribution for women, and this would be the distribution for men. In any case, you can see this with birth weights, elevations of Venus, interestingly. So the elevations of Venus, if you take, you know, you think about, okay, I'll use this as an example. This would be where the majority of, this is the elevation of most of the surface of Venus. Some of the surfaces are a little bit higher, some of the surfaces are a little bit lower, but in general it looks about like a normal distribution. Interestingly, Earth does not have a normal distribution when you're talking about the elevations like that. And it comes from the fact that there's a difference in density between continental crust and oceanic crust. If you restrict yourself just to continental crust, it looks like a normal distribution, or just to oceanic crust, you get a normal distribution. But when you try to put them together, you get something similar to like with the women and the men. You get, you know, you get a little bump and then it goes down and then there's another little bump. So your oceanic crust would be down here, your continental, no, oceanic would be lower, less dense. No, your oceanic is more dense, lower elevations, whatever. I'm moving on. All right, every normal curve, let's move this where you can see it. Every normal curve has the following properties. All right, so the peak occurs directly above the mean. You can see in these examples right here, I have the mean occurring right in the middle, and that's where the peak is. They are balanced about the mean. I guess I didn't say that, but I did say it. Well, I guess you can get that out of this next one. The curve is symmetric through this vertical line, so these lines that I drew in, the curve is symmetric. If I was to fold the paper or my screen, well, that would be bad if I folded a screen. I did this on paper originally, but if I was to take this and have it on paper, I folded it over, this part of the curve would exactly match up with this part of the curve, and vice versa there, and similarly there and there. It never quite touches the x-axis. Now, it'll look like it touches the x-axis because it gets so close, and something like this, I mean, when you draw these, yeah, you'll probably end up accidentally having it touch the x-axis, because who can who can get that close to two lines and not have them touch? But the curve never does quite touch the x-axis. It always sits just above, even as you go out to, you know, negative 10 million in this direction. It'll still be just above the x-axis. It'll get arbitrarily close, but never quite touching. The area under the curve, between the curve and the x-axis here, is always 1. This is, as I was describing on that last page, your total area is 1. The total probability is 1, and we express the probabilities with areas here. So the total area is also going to be 1. Normal distribution is completely determined by its mean and its standard deviation. So when we're talking about one of these, the only two values we need are the mean and the standard deviation. Once we have those, if we know we're talking about a normal distribution, we have everything that you could ever want, ever need for it. And then lastly, the area under the curve. So when we're thinking about one of these normal distributions, if you're trying to figure out the probability of being at any exact value, because this is a continuous distribution, the probability of being exactly any one value is essentially 0. Well, it is 0. You know, if you kind of go back and think about that previous page, if I was to take and divide out my, divide this smaller and smaller, each of these bars, in order for the total sum to be 1, each of these individual bars would have to contribute less to the total. Therefore, they have less area, and therefore, essentially, once you have infinitely many of them, each of them would have to have an area of 0. Again, this is getting into the realm of calculus. If you're interested in the whole adding infinitely many things with an area of 0 each, that is a classic calculus problem right there. In any case, what we're interested in here, if we say we're trying to find the area, or trying to find the probability of some value being between A and B, we'll generally draw it like this. So A is somewhere here. It looks like it's slightly above my mean. B is somewhere over here. If I'm trying to find the area that I'm being between A and B, I would find the area under the curve between those. That's how we represent that's how we find the areas here. And we're going to go back and forth between calling this a probability and an area, because those do represent the same idea here.